everyone, welcome back to Codviento. Binary trees are the heart of the coding interviews. But do you actually know the difference between DFS and BFS? And how traversals like pre-order, in-order, post-order, and level order really work? Let's break them down clearly, visually, and with real LetCode examples. A binary tree is a special type of graph where each node has at most two children, a left and a right. And how do we explore this structure? That's where DFS and BFS come in. DFS, depth first search, explore deeply down one path. BFS, breadth first search, explores level by level. BFS traversals, pre-order, in-order, post-order. BFS traversal, level order. Let's deep down traversal details by examples and pseudocode explores. Pre-order traversal. Visit the root first, then the left child, then the right. Let's traverse the example together. We visit node 1 first. It is a root, so we add 1 to our result list. Now we move to left child of 1, which is the node 2, and we visit it. From node 2, we again go left node 4, visit it. Node 4 has no children, so we return back to node 2. Now we move to the right child of 2, node 5, and visit it. Node 5 has also no children, so we return again to the root node, node 1. Finally, we move to the right child of 1, which is node 3, and visit it. Result is 1, 2, 4, 5, and 3. We always visit first root, then explore left, then explore right. That's what makes it pre-order. Let's check the pseudocode together. Pre-order recursion. If root is equal null, return. Visit root. Call pre-order left and call pre-order right. In-order traversal. Explore the entire left subtree. Visit the root, then go right. Great for sorted output in binary search trees. Let's traverse the example together for in-order traversal. In order travels, we always go left first. Then we visit current node root, then go right. Let's check the example together. Start at root node 1. We don't visit it yet. In order says go left first, so we move to node 2. Again, we follow the rule, go left first. Move to 4. 4 has no left child. We visit it. Back to node 2. Left of 2 is done, so we visit node 2. Go right of 2. Node 5. Node 5 has no children, so simply visit it. Back to root. We have finished the left substrate of root, so we visit the node 1 now. Go right of root, node 3. Node 3 has no children, so we visit it directly. Final in-order traversal output is 4, 2, 5, 1, 3. In-order is great for binary search trees. It returns not in sorted order. We always go left, root, right. And that's exactly what we just did. Let's check the pseudocode together, its recursion. In order. If root is equal null, return. Recursion call root.left. Visit root. Recursion call root.right. Post-order traversal. In post-order travels, we always explore the left subtree fully, then the right subtree, and visit the current node last. Let's traverse the example together. Start at root 1, node 1. We go left first, move to the 2. Follow the rules. Left first, move to 4. Node 4 has no children. Both left and right are empty, so we visit it. Go back 2. 2 has right children, so go right. Node 5 has no children, so we visit it. Now that left and right of 2 are visited, so we visit node 2. Back to root, and root has right child. Go right, node 3. Node 3 has no children, so we visit it. Now both subtrees are visited. Visit root. Finally, we visit the root node 1. Last step. Final post-order traversal output 4, 5, 2, 3, and 1. Post-order traversal is useful when we want to delete or free up a tree. Let's check the pseudocode recursion together. If root is equal null, return. Recursion call for root left. Recursion call for root right. Visit root. Let's check level order traversal together. Traverse the tree level by level using a queue. Perfect for shortest path, layer-based logic. Level order travels means we visit nodes level by level, from top to bottom, left to right on each level. To perform level order travels, we use a queue. because the queue processes nodes in the exact order they appear, first in, first out. We enqueue the root node first. We remove node 1 from the queue and visit it. Then we enqueue its children 2 and 3. Now we process node 2, visit it, and enqueue its children 4 and 5. DQ 3, visit node 3. It has no children, so nothing new is added. DQ 4, no children. DQ 5, no children. At this point, the queue is empty. We visit every node level by level. Final level order traversal output 1, 2, 3, 4, 5. Notice the difference. This traverse doesn't go deep. It sweeps left to right at each layer, then moves down. It's perfect when the problem mentions levels, short path, or grouping by depth. Let's check the code together. If root is equal null, return. And create a queue. Add the root to queue. While queue is not empty, pull the queue's first element. Visit the current element. If the current element left child, add the queue to left child. If the current element is right child, add the right child to queue. So which one should you use? Pre-order cloning or saving tree structure. In order, sorted data from binary search tree. Post-order deletion cleanup. Breadth first search, level order, shortest path, layer order logic. If the problem involves levels or minimum steps, go with breadth first search. If it's about fully traverse or recursion, stick with depth first search. Let's check real LetCode examples together. In this video, we will solve LetCode 144. It's a classic problem that helps you understand how depth first search works in trees. And a very easy problem to understand binary tree pre-order traversal. Given a root of binary tree, return the pre-order traversal of its nodes values. Pre-order means visit the root first, then the left subtree, then the right subtree. Let's look at the first example in the question. In this tree, we start at 1, then go right to 2, then left to 3. So, pre-order gives us 1, 2, 3. Let's check the code together. Here is the tree node definition, integer value, left and right tree nodes, an empty constructor, constructor with value, constructor with value left and right. Let's check the code together. We'll define a result and we define a helper method and we will return the result at the end. Let's check the helper method together. We define a helper function that takes the current node and the result list. If the node is null, we return. Otherwise, we visit the current node by adding its value and the list. Then we call the same function, recursion, on the left and right child. Now let's run this code and check the result together. Perfect. Code runs successfully. It works for examples and passes all the test cases. Let's submit the code and see the result together. It's perfect. Time complexity is O(n), where n is the number of nodes since we visit each node once. The space complexity is also O(n) because of the recursion stake in the worst case. If this helped, check out the in-order and post-order traversal videos next. And don't forget to subscribe if you want more clear Voltron like this. We'll solve netcode 94, binary tree in-order traversal. This is one of the most common depth first search pattern and very useful in binary search trees. The task is simple, return the in-order traversal of a binary tree. That means left, root, right. Let's check the first example together. For this tree, the in-order traversal would be 1, 3, and 2. We first go as far left as we can, then visit the node, then go right. Let's walk through the steps. Start at root 1. No left child, so we visit it. Go right to 2. It has a left child 3, so we visit 3 first. Then visit 2. This pattern works great in binary search trees because in-order traverse gives value in sorted order. Let's check the code together. Here is the tree node definition. Tree node has a value, left and right nodes. No constructor definition, a constructor with value left and right nodes. Let's check the code together. We define a list integer result. We will return the result. We define a helper method with 3 nodes and result. Let's check the helper method together. If the node is null, return null. The first, we call the function on the left child. Then we visit the current node. Finally, we explore the right child. Let's run the code and check the result. Perfect. And let's submit the solution and see the result together. It's perfect. Time complexity is O(n) since we visit each node once. Space complexity is O n, do the recursion stack. This is in-order traversal, clean and simple. If you like to learn pre-order, post-order or breadth-first search as well, check the links below. We also LetCode 145, binary tree post-order traversal. This traversal explores both children fully before visiting the parent. This makes it unique and powerful in some use cases. Given the root of binary tree, return the post-order traversal of its nodes. That means left, right, root. Let's check the first example together. For this tree, we first go to the left of 2, not 3, then back to 2, and finally visit the root 1. So the output is 3, 2, 1. Let's check the code together. Here is the definition of tree node. An integer value, a left node and right nodes are defined. An empty constructor, a constructor with value, and left and right nodes. Let's check the code. Okay. Here we define a list integer result and we will return result. Post order is a helper method with tree node and list result. We check if the node is null, return null. First go left, then right, and only then visit the current node. This is completely opposite of pre-order. Let's run the code and see the result together. All the tests are passed, and submit the solution, see the result together. Perfect. Time complexity is O(n). We visit each node once. Space complexity is O(n) because of the recursion stack worst case. That's how post-order travel works. Notice how long it takes to reach the root because we only visit it after everything else is done. Now that you have seen pre-order, in-order and post-order on the same structure. To complete the full picture, watch the pre-order, in-order and breadth-first search videos linked below. And don't forget to like, subscribe if you found this helpful. We also LetCode 102, binary tree level order traversal. This is the breadth-first search problem, where we traverse the tree level by level instead of going the deep first. The task is to return the value of each level in a binary tree as a list of lists, from left to right, level by level. Let's check the first example together. We start at level 0, just 3. Next level, level 1, 9 and 20. Then the last level, 15 and 7. So, the output will be list in the list 3, 9, 20, 15, 7. To solve this, we use a queue. It helps us process nodes in order of their depth. NQ root 3, DQ 3. NQ 3's children, 9 and 20. DQ 9, no children. DQ 20. NQ 20's children, 15 and 7. DQ 15 and 7. At each step, we track how many nodes are in the current level and process them together. Let's check the code together. Implementation in Java using a queue. Here is the binary tree node definition. Tree node class, integer value, left and right nodes, no args constructor, a constructor with integer value, a constructor with integer value, left and right nodes. Let's check the code together. This is the final result. It will contain one list per level of the tree. If the input tree is empty, we return an empty list immediately. Now we use a queue to help us traverse the tree level by level. We start by adding the root node into the queue. We continue the process as long as there are nodes to process in the queue. We check how many nodes are currently in the queue. That tells us how many nodes are in the levels. We also create a temporary list to store value for this level. Now we loop exactly level times size. So we only process the nodes in this level. No more, no less. We take out the node at the front of the queue. This is the node we are currently visiting. We record its value in the level list. This is what we will return later. If the current node has children, we add them to the queue. But notice they won't be processed now. They will wait for the next loop iteration, which will be the next level. After we process every node in this level, we add the level list to our final result list. When the query is empty, meaning we have visited all the nodes, we return the result. Run the code and see the result. All the tests are passed. Submit the solution and see the result together. It's perfect. Time complexity is O(n). We visit each node once. Space complexity is also O(n) from the queue and the result list. This is how level order traverse work with breadth-first search. If you want to go deeper into depth-first search strategies like pre-order and in-order, check the links below. If you enjoyed this video, please don't forget to like and subscribe. Thank you for watching, friends. See you in the next one.